let me start, of course, with a special thank for accepting to be our guest in this interview. You know, some scientists, as soon as become famous or they get a very prestigious award, as you did, they are not so available to spend time with young scientists, to talk to them and to spend time with them. So, first of all, once again, thank you very much for accepting our invitation. And let me just also spend a few words about the meaning of this interview. We want to, let's say, have a key message to share with the young member of our division. As you have learned during these days, we are the Electrochemistry Division, but we are part of a bigger society, the Italian Chemical Society, and maybe all of them are interested to listen to your point of view about several themes, several topics, and so on. So thanks again. We have asked young scientists of the society to make a list of questions, and we selected a few of them, and we will ask this question to you as soon, in a couple of minutes, I mean. Of course, I left also a few minutes for me. I'm not so young, but I want also to ask a few questions as well.
It's all relative.
Yes, that's a good point, yes. And so let me start with, let's say, maybe the most frequent question that came from the audience. First of all, who are the scientists or other personalities, I mean, that in some way influenced your path, your choices, let's say, on a scientific point of view, but also generally speaking in your life, that allow you to take a few decisions?
Well, they're originally my two high school teachers. I had a physics teacher called Squibs Bowman and a chemistry teacher, Major Lamb. And they got me all excited about chemistry. Then I went to Oxford and had Peter Dickens as a tutor. So in Oxford, you write an essay each week and you spend 1 hour discussing it with your tutor. And he was very enthusiastic. Then I did my bachelor's degree with him, then my doctorate with him. So he got me all excited. And then after that, I went to California, to Stanford, where the sun shines. It doesn't shine much in Oxford. And 2 months later, my advisor there, Bob Huggins, left to go to Washington. And he said, "Stan, you're running the group for the next 2 years." So he gave me the confidence that I could do this. And it's exciting times then, because America was putting lots of money into science, because the Russians had put Sputnik up there and they wanted to catch up, and it was mostly material science. So it's a very exciting time.
Your name is mainly linked, of course, to lithium-ion batteries because of the price, of course.
Right.
But can you share with us if there are other scientific achievements that made you happy but are not as popular as lithium-ion batteries?
So my interest has always been how ions move fast in solids. So this was the interest at Oxford when we looked at tungsten bronzes and ions moving through those. Then at Stanford, we looked at how ions moved in beta alumina, which was of interest then as a battery electrolyte. And at that time, the field was just getting going. And we had the first international meeting on Lake Maggiore in 1972. So just over 50 years ago. So that's when the field really started. And it was only then that chemists and physicists got involved in the battery area. There were no chemists and physicists, it was just battery electrochemists before that. So that really got the field going again. But I've always been really interested in how do you make new materials? By soft chemical approaches, not by high temperatures. So we can make new materials by putting ions into a material or taking ions out. Electrochemical was one way of doing it. You could also do it using chemical methods. So it's what we call soft chemistry. So it's the same thing about how batteries operate. We want to operate them at room temperature.
Did you immediately realize that your discovery would bring a big revolution to the field of electrochemical energy conversion, but generally speaking to the field of energy conversion and storage?
Well, we were trying to build a clean energy environment, and this was Exxon, the oil company. They want to be an energy company, so we were trying to make fuel cells. We wanted to make lithium batteries to to make electric vehicles. Remember, there's no such things as phones or any other of these devices back in 1972. Even the computers were tiny. They didn't do anything. So our real goal was to make electric vehicles. Exxon, in fact, bought an electric motor company so they can make electric motors. So we had some good ideas, but like all R&D ideas, there were hiccups along the way. So they decided, for safety reasons, they'd make small batteries for smartwatches. In those days, the watches used LED displays rather than LCDs. So you had to recharge or change the battery every week. So they wanted to recharge the battery, and that's where they tested them out originally. But their goal was electric vehicles. We didn't really, no, half the things they used for the day we hadn't even dreamed of. There's no talk really of grid storage back then. You say no devices, and there's only 10 years later, 10 to 15 years later, that Sony wanted a good battery for their Walkman and other toys. That was many decades later.
So a completely different scenario, I mean.
Yes. So they really became popular in those small electronic devices, and that's where they got commercialized first. But Exxon did build an electric vehicle. It had lead acid batteries in it. It moved, but the goal was to put lithium batteries in that vehicle.
Do you want to share with us your opinion about the trade-off between improving an already existing technology or investing in the development of new ones?
I think the challenge we have today, lithium-ion batteries are here, but they're not here. They're all made somewhere else. So to really make an impact on, say, electric vehicles or grid storage to enable renewable energy, we've got to start making the batteries in the location where they're going to be used. Because right now it takes 60 to 80 kilowatt hours to make a 1 kilowatt hour battery. And some of the materials travel 20, 30,000 miles from the mine to the finished product. And that's not sustainable. So I think we need more effort in how do you make clean materials, how do you make them locally. And that may mean we'll have different chemistries, say in Europe than America than in Asia. So we'll have to match the chemistries to what we have in our own regions.
So also the technological development is a key point, I mean.
Yes, very much. And I think key thing happened, was it 2 weeks ago, when Apple announced all the cobalt in all their devices is now recycled cobalt, so no longer getting cobalt from any mine. So you're using totally recycled cobalt. And then in the end, that's what we have to do with all the batteries, totally recycled.
Now, if I may, I want to ask you a few questions, which are, let's say, a little bit more personal, if I may, but feel free to not answer if you feel that they are not suitable. Did your working life change after winning the Nobel Prize? The feeling from the colleagues, from your students, also from your friends, I mean?
Well, clearly it changed. People listen more now. And the politicians come calling more. So soon, I was in Germany at the time that it was announced. And I think within half an hour, the mayor from Germany was at the meeting. He clearly wanted his picture on the morning newspaper. But I think, I go to meetings now, people want to know what's important, what's not important. And everybody wants their picture taken. So all that kind of thing has changed. But we can more easily get money from the government now to do what I call this transition from lab R&D to manufacturing. So we raised about $113 million to build a prototyping facility 4 miles from the university. And that will help people with ideas make prototype batteries before they go to a big gigafactory. So those kind of things that help. But I got the Nobel Prize just before COVID came. So ours was an unusual class, I think, because normally we'd get inundated, please come here, please go there. And there was none of that. So there's one day I gave a talk in London at 9 a.m. in Washington, D.C. at noon than in Japan at 7 o'clock at night. So more talks, but got rid of most of the travel.
The job of a researcher, and you of course know about it, is quite heavy. I mean, it takes time and you have very small time for your private life. Do you have any regret about what you did in the past, about your choices, if I may, of course, ask?
There's always pros and cons to everything you do. So my wife stayed at home to raise the children until they were old enough. Then she went back to finish her PhD, then went on to be chair of her department. She does now in languages. So there's challenges there balancing two professional lives. And obviously the Nobel Prize doesn't help that. There's even more pressure on.
But you succeeded, I mean,
yes.
in balancing both aspects.
Yes.
And the end is really successful, so maybe
Right.
this is also a good message to pass to young researchers.
Yes.
That maybe they have to face a lot of difficulties in balancing the duties with the family and duties with the job. I mean.
Yes. But I remind all young researchers, we have children, they grow up and leave the house much faster than you ever anticipate. So spend time with them when you can.
As a Nobel Prize winner, you will be, and you are, a model and a source of inspiration for all the new generation of scientists, and especially the one working in the electrochemistry and the battery field. What are your feelings about that? It's more an honor, responsibilities.
Well, I've always liked teaching young scientists, particularly the ones brand new to the university. They're all still excited, and my job is to keep them excited and not, let's say, bore them with detail. So when I teach chemistry or electrochemistry, I eliminate the first 150 pages of the book because that's boring. Let's get into the real stuff. And in ITH, I always use real examples of real life, not, we balance this equation to get this, why are you doing it? So a typical example we do when we discuss, say, the ideal gas law, PV equals nRT, I said, how many grams of sodium azide do you need to inflate that bag in your car if you get in an accident? And as soon as they understand why they need to know these things, then they're much more involved. So I don't treat it as a theoretical. Let's get involved. And I said, do things you're excited about doing. My message to all students as they graduate, don't do things for the money. Do it because you want to do it and it excites you to do it.
The very last question is why we are here. So, do you think that the communication of science outside from the scientific community is very important today, or that the most important part is only the experimental results that you obtain in lab?
So, at the Nobel ceremony, each group has to give a 3 to 5 minute talk at the banquet. And one of my messages there, that science is interdisciplinary, so you interact with other people. It's very much international, but the final message is facts matter, and your job is really to teach or communicate with your parents, your community, why science is important, why climate change is real, and help to recommend to politicians what they should do. Don't tell them what to do, because they won't do it then. But you've got to educate the general population, so just doing the experiments is nowhere near enough. You've got to do experiments, you've got to publish in the right place, which means a scientific journal, but also the local newspaper. We kind of have science cafes where we'll have a topic for discussion, and the local newspaper will publish it. We make it 50 or 60 people show up in the evening just to listen. I think that's very, very important. We've got to communicate our science to everybody.
Okay. And which is the most difficult? Communication to everybody or communication within scientific community?
The most difficult is getting the experiments to work. Because this is what most new researchers don't realize. as a student, the experiments are being designed, you know they're going to work. But as a researcher, probably 2/3 of them don't work. So you have to, do the ones that do work, then ones that don't work, you've got to work out why they didn't work. You may learn far more from those that don't work than from the ones that do work. So I think doing the experiments is the hardest of all, because you can get very frustrated when they don't work. And young students probably get the most frustrated. This isn't working, that's not working. What do I do next? And I tell the students, I'm not going to tell you what to do. Here's the big picture, you tell me what you're going to do. What's your hypothesis? Then go out and test it. But I'm not going to treat you like a technician. And I think that's important.
Technically, these are the question we were thinking on. Right. Of course, if you have some specific topic you want to discuss with us, we are open to make a few questions, specific question on your request. I mean, this is something that was...
Well, you can add the question in afterwards, right? So one thing I think is important is meetings of this size. You have your Italian Chemical Society like we have our American Chemical. Thousands of people there. You don't get to meet people. And if you have meetings of, say, 100 people with the Gordon conferences, the students get to meet the big names in their field. They get to interact with them, have lunch with them, have dinner with them, so they can understand the real challenges. So I think it's important we mix, shall we say, the chiefs and the beginners, so they'll know each other, can learn from each other. But the real message is do things because it excites you to do it. And we used to have a summer program where we brought in undergraduates and a few faculty from other places. Maybe we had 20. At the end of the summer, 3 to 5 would say, I didn't think research was like this, I don't like it. And I said, we've done you a great service. You spent 10 weeks here, not 5 years getting a PhD, then saying you didn't like it.
We thank you once again, and we will share these very nice words with the young members of our society. And thanks again for being with us. Thanks a lot.
Sure you will. Share it with the more senior members too.
Of course I will. I will.
Yes.